we're connected. I don't want to change my background. We're going live in perfect. Okay. Do you guys see me or do you see a nationwide live stream party?
On the screen sharing, we see the live stream, kind of like the poster, and then I see you as a
Great.
one of the galleries.
Yep.
Okay, great. Are you guys all galleries too? It doesn't let me see what I'm looking at, which is highly unfortunate. I can't see what you guys see.
Yeah. Yeah, I can confirm.
Okay.
I would definitely see you, Daniel, Brian, and then Shannon, Jerry, and I don't have video going.
Great. Okay. So
people are posting.
Hi there, everybody. So we're actually live now. So if you guys talk, you are going to be live. So I would mute your audio. Mike, if you want to mute your audio as well, Mike Keefe, and we'll get started right now. So welcome everyone to the nationwide live stream star party. And we're so happy to welcome you here tonight. We have a great lineup of presenters for you tonight. My name is Amy C. Oliver. I am the Visitor and Science Center Manager at the Fred Lawrence Whipple Observatory, part of the Smithsonian Institution. And we also have with us tonight several members of the NASA Solar System Ambassador Program, and later one of our presenters is going to tell you all about that program. We have with us Mike Keefe, the astronerd, and we will have John Carter from the Prescott Astronomy Club, Shannon Morgan from MSRO, which is the Mark Slade Remote Observatory. We have Daniel Cervantes from the Feynman Observatory, and Brian Cummins, who is also a solar system ambassador with us. So let's see if we can get this running. All right, so as I mentioned, we have a great list of presenters this evening, and you'll be watching us scroll through some of that right here for just a second, so that you can get a good idea of who's with us. So great backgrounds from everybody, and we're really excited about that. And before we get started tonight, there's some things that I want to talk to you about the night sky and about how our evening is really going to go. This is not your normal star party. Okay, so obviously, you know, you're sitting in your living room. You might be like me, you're having a nice hot cup of tea, my little sloth in my nice little mug, right? I'm in Arizona, so I've got my cute little cactus mug rocking. I'm waiting for my tea to finish. You're, you know, depending on where you are, if you're on the East Coast, you're curled up in a blanket. If you're over here on the West Coast, down in Arizona or Texas, you know, you're sweating to death. We've already got our air conditioners on, but you can still go outside and see some things for yourself, okay? So if you are in Arizona or somewhere closer to Pacific time, so you're in, you know, Utah and Mountain Time, or you're in California, Sacramento, if you go outside about 9:30 tonight, and you look to the east, and you look up above the horizon line, you're going to see these types of constellations. Okay, so well, these exact constellations, right? So I've pulled this for you for this exact time tonight. You're going to be able to find Hercules. Lyra will be just coming up over the horizon line, and that's where the Lyrids meteor shower is peaking. So it peaked just earlier in the week, but you might still catch a shooting star if you engage in dark adaptation. That means turn out all those white lights inside and outside of your house, and then stay in the dark for 10 or 20 minutes, and then look up into the night sky, and you will see this beautiful, beautiful night sky filled with stars, and you'll very easily be able to look for this, the radiant point of the Lyrids meteor shower, which is where those meteors will appear to be coming from and shooting at you from in space. And you just might see a shooting star. Now, you can also see here, there's some others that you might be able to see as well. So give it a go. Now, if you're on the East Coast, you might see something a little bit different. And that's due to your latitude and also the time of night. So the way that we are moving through space, you're seeing a little bit different portion of the sky than the rest of us. And that's what's so cool about this star party tonight, where we have presenters on the East Coast, right? That they are seeing things in the night that haven't yet risen for those of us on the West Coast. That's pretty exciting. It's a really, really cool time to be engaging with this type of star party where we all can come together. And I didn't mention to you before, but we have presenters tonight from Arizona, Virginia, North Carolina, and Indiana. So you're getting almost all of the time zones. And so you're seeing this different swath of the night sky. I also want to point out to you tonight that the weather's not the same everywhere. So we have extraordinarily clear skies in southern Arizona tonight and in northern Arizona, where John is from. Indiana isn't quite experiencing that beautiful weather that we're having. It's already summer for us, still kind of winter for Indiana and for some of the East Coast. So bear with us tonight, and we have a backup plan for anyone who gets clouded out. But if you are on the East Coast at about 11:30 tonight, so in just about an hour and a half, you'll be able to go outside and you will see Aquila, the eagle to the east. You can see it here in the image. You'll be able to find Cygnus, the swan. And what's really wonderful about this, this swath of constellations is that if you are in a dark location, you'll actually maybe get to see some of the Milky Way. So some of our presenters are even out in very, very dark sky locations tonight, and they might be able to see that swan and the eagle flying across the Milky Way. And I'll be very excited for them if they get to see that tonight. Now, what we're hoping to see is some very exciting things. Okay, so what you're seeing on the screen now is the comet Atlas on our left, in the middle, the Owl Nebula, and then a galaxy. Okay, so these are all very beautiful images, and we are hoping to be able to see a very wide array of these types of things tonight. Just one comet, because we just have one to be able to target at tonight. And that's okay, because it's a very exciting moment to be able to see something like this in the night sky. It's not very apparent to the naked eye, and so there's not somewhere we can just point you to and say, look at this. And so the Mark Slade Observatory is going to help us look for this object tonight. And then we have other presenters going after some of these other types of objects, nebulae and galaxies tonight. So what is a galaxy and what is a nebula? Okay, a nebula is a very gaseous cloud, and it is tied to the life of just one star. So when you see these beautiful images like the one on the right of the nebula, those pinks and blues and purples, all of those gases and those colors are created from one star, in the life of just one star. When a star goes supernova, it can create this beautiful nebula and this birthplace for stars. So it's really a stellar nursery. So it is tied to that one life, but then can generate other lives over time. A galaxy is significantly larger, times and times bigger than nebula, and they are tied to the lives of many stars. There are sometimes millions and billions of stars within a galaxy. We live in a galaxy. And the Milky Way galaxy, so if you've ever gone outside and seen an arm of the Milky Way galaxy, you're just seeing some of the stars, some of our stars in the Milky Way galaxy. Okay, now, it's also important before we get started that you understand what we're actually going see through a telescope. Now you've already seen, I showed you a picture of the Owl Nebula. And I'm showing it to you again here on the left. Now when we see it later through a telescope, well, and Mike's probably over there wagging his finger at me like, don't ruin the surprise. But you're going to see something a little bit different. Sorry, I just nearly fell out of my chair for you guys tonight, but how excited I am. Can't sit still. But more like the image on the right. Okay? So these images that are big and beautiful and bright and full of colors are not necessarily what you would see when we're using a regular telescope. When you put your eye up to the eyepiece on a telescope. And there's a good reason for that. As human beings, we see with rods and cones. You can see this image here, very scientific image, kind of zoomed in on how the eye is constructed. The rods are the blue, right? And they look like a tube, they look like a rod. And those teal things have a point at the top of them. Those are cones. Now, rods and cones help us to see different things. Our cone cells in our eyes help us to see color and patterns and all of the details that make leaves and flowers and nebulae very exciting. Now, rods, on the other hand, help us to understand shapes and objects in the dark. So our cones rely on a lot of photons and a lot of light to be able to see color and to see patterns and to see detail. Our rods, on the other hand, work for us in low light. So if you've ever walked through your house in the dark and you can sort of see the shape of the couch before you trip on it or stub your toe, you can thank your rod cells for that. But so in low light situations, that means that you are likely not going to see those deep, bright colors. So what's with this image? What's with this beautiful image of UGC 1378 taken by the MMT telescope at my facility at Fred Lawrence Whipple Observatory that is all of these colors of this galaxy, and there's so much detail and you can see all of these stars and everything going on and all of this color. Well, let me tell you a secret. What's happening is that the MMT, first of all, is 6.5 meters in diameter. That's like almost 22 feet. You are not the giant from Gulliver's Travels, and you do not have a 21.5-foot iris to collect light while looking into the night sky. Okay. The other thing is that the MMT took this exposure and has taken many others like it of other objects in the night sky over a long period of time. I know that I would not sit with my eye glued to an eyepiece on a telescope for 8 hours without blinking. If there is someone out there that can do that, you please let me know. Okay? So if you would do it, we're going to give you a job. But otherwise, it's important to know that that happens. Also, we rely on spectroscopy, and we rely on other tools to sometimes help automatically color in images. So a couple of our presenters tonight are going to talk to you probably about stacking and about the way that we make images look the way they're supposed to look. And they'll explain why that happens and how we do those types of things. So these images that you're looking at are not something you're just going to see with your eye by looking straight through a telescope. We're still going to see really cool things, and I think you're going to be really amazed. So without further ado, we're actually going to start by handing it off to our friend Daniel Cervantes at the Feynman Observatory in Indiana. And give me just 1 second, and we're going to get that all taken care of. All right, Daniel, I think you are ready to go whenever you're ready.
And you just need to come off mute.
Okay, here we go. Now, let's see. I'm Dan Cervantes, and I'm in Indiana, and I'm the owner of Feynman Observatory. And in addition to that, I'm also a solar system ambassador, which is what Amy is, and a number of us are here. And we do a lot of outreach for the NASA and Jet Propulsion Laboratory. And because we're clouded out tonight, which sometimes happens, especially in the Midwest, I'm just going to show you a short brief of the observatory and talk about some of the outreach activities that we do, which are really useful if you're a educator. So if you have kids and you want to have some kind of a program set up to expand on your science activities, and you want to do some observing live, we'll talk a little bit about what you can do. So, and also if you're a community member and you have some kind of community group and you also want someone to talk to about NASA and what they're doing in the solar system, and maybe you want to look at the sun or some other objects, we can set something up for you. So let's see if I can share here. Somebody may have to help me here. I need to share my screen. And I don't see the function here. It's down at the bottom. Mute, security. Amy, can you help me here? I don't see a share button.
It should be at the very bottom of your screen. There's a little green kind of up arrow in a box.
Ah, okay. Yeah, oh, sure. All right, this is the second time I've done it now, so I'll hopefully get it after this. Okay, let me make sure I share the right screen. For some reason, I put this thing up on the wrong screen, but I'll go ahead and do that and share it, and we'll see if we can get this thing started. Am I sharing the screen that really has you on there right now? Amy, can anybody see the shows the share?
Right now we're just waiting for your screen to share. So I think
Okay,
as soon as it does, we'll be okay.
I think we got it.
You are perfectly fine now.
Okay, let's see. Come on. Well, I won't use the remote, so we'll just start it manually. It was working today. Okay, slideshow. Let's start it from the beginning, and hopefully it's sharing it to you there. So you should be seeing a picture of the observatory. This is basically just in my backyard, and I named it after Richard Feynman, who is my favorite physicist. He was, as well as a Nobel laureate, he was also a great educator. He took very complicated ideas and made them very simple. So even though he wasn't an astronomer, I still named it after him. It's got a picture here of an old telescope that has since been replaced. It was replaced last year. This is an old 140 millimeter refractor that was primarily used the last 5 or 6 years for solar observing. But since I also like to do a lot of planetary work, I upgraded, and we did that last year. And this is basically what we put in. We put in a 300 millimeter, which is about 12 inches. And it's a specialized, sort of an unusual telescope. Not too many people really even use them anymore. People often ask me why I did, but they're basically designed for looking at high magnification. You don't have to have a lot of extra glass between what you're looking at and the thing you're looking at. So you don't have to put a bunch of extra lenses in to increase power. It's really just meant for looking at small, bright objects like planets, asteroids, those kind of things. So that's really the purpose of it. I've expanded a little bit more into doing a few deep sky objects, but because it's such high magnification, you really need to take long images. So it's really not designed for that, but I've had a little bit of luck, and it's kind of fun. So to expand upon what I've done in the past. So we put that in last April. So it's just been about a year now. So I think I took that picture right when we did it. And we also updated after that, we started to update some of the camera equipment. So basically now we can do a lot more serious imaging, which was something we could never do in the past. A new camera, which is collects light a lot quicker, some electronic filters, so you can adjust the filters remotely, some guide cameras, some camera rotators, and most important for me, and what really will help me tremendously over what I was able to do before, was we have electronic focusing. And having not the best eyes in the world, not a lot of contrast in my eyes, focusing has always been a problem for me. So going to electronic focus for me is a major improvement. So talking about solar observing and imaging, really that's what this presentation is really sort of about. We're not going to talk a lot about the sun or a lot about imaging the sun, but we just want to show you what the capabilities of the observatory is, because as I mentioned earlier, we can use that as part of the presentations. So sort of out of the problems that we've had lately with social distancing, I never really did any social broadcasting of any sort, but I found that this is really interesting, and I think a great way to help to get some of this stuff directly into schools. In the past, we had talked about bringing in solar telescopes to the schools, but there's a lot of problems with that. Not only is it heavy, lots of equipment, but if the clouds move in, it's all for naught. Plus some students also, some teachers don't like their students to basically look at the sun. They're afraid of that, or maybe they're the principals or the staff kind of get a little nervous about that. So this kind of eliminates that, because we can now broadcast this directly to the school through Facebook Live or other methods too. But we've got a couple different ways we can do it. And now that schools are pretty familiar with all those tools, this should be easy. So basically, I mentioned before, we pulled out our solar telescope, but as of Monday, we should have the parts to remount it back on top of the larger telescope. So now we'll have basically two telescopes in there, and I still enjoy and miss doing the solar observing. Hydrogen alpha filters are what make this telescope unique. And they are a filter that basically takes out a lot of the light that you get from the sun. The sun basically goes from about 4,000 to 7,000 angstroms from blue to red. And this just allows a very small portion of the red to come through, and it allows you to see the chromosphere, which again, I'm not gonna have a lot of time to speak about these things right now, because that wasn't the purpose of this. It was to do live observing, and I don't want to spend a lot of time and take it away from our folks here who are going to be able to show that to you later. But the capability is that looking at the chromosphere, which is a very thin layer that lays above the normal part of the sun you see, is very active. And these are just a couple images taken previously through the telescope that'll give you a rough idea. What you're looking at here might be a little hard to understand, because the actual sun itself is blackened out here. So what you're seeing, and that's done for a reason, you have to overexpose the main disk of the sun to get the chromosphere, which is just above the sun. So you see all this weird hydrogen gas that's floating above the sun, and these things rise and fall and change over very short periods of time. So it's a very active thing to look at. And that's all in the chromosphere. And it's just a very thin layer above the top of the sun. But having these hydrogen alpha filters and a relatively large telescope to look at it, we can really get some very good images. And these are just a couple examples. I never really did a lot of photography back before, something we're moving into now, but this will just give you a glimpse as to the kind of things you're going to see. Now, here's what the filter basically consists of. It's a relatively good sized filter, and as you can see there, it says something about 0.8 angstroms. That's how much of the light it's actually letting in. So imagine you got light going all the way from 400 or 4,000 to 7,000, and you've got 0.8 angstroms basically of light. So that's a very small piece of it. And that's what those pictures were taken with this 0.8 angstrom filter. That was originally picked because I didn't know how much light would be allowed into the camera. And so I sort of went for a slightly wider filter to get more light. And it turned out we've got more than enough light. So now what we've done, and it only occurred accidentally, 2 weeks before we were swapping out the telescope, the filter went bad. Well, these filters are designed by people that do a very good job of making sure that they work for the 10 years they say they're going to. So they said, well, we'll replace it, don't worry about it. And so we took the opportunity to upgrade. The problem was I only got to use it for 2 weeks before we swapped the telescope out. It is significantly better than
Daniel,
8. Yes.
we have a question for you.
Yes.
From, looks like the username is Paige Else. Does the roof slide off of your observatory?
Yes, the roof does slide off the observatory. It's a roll-off roof observatory, and those are fairly common now because they allow all the heat to sort of, whenever you observe, especially at night, well, during the day too, you want everything to be at the same temperature. So people have sort of gotten away from the old-fashioned observatories and gone to these roll-off roof. And someday, if I ever give a presentation on it, I cut all these slides out. I had one of it rolling off, but it's basically, you just push a button and it's got a motor and it just drives it off. So it takes, I don't know, 30 seconds or something for it to roll off onto those rails that, well, I don't know if you probably could see the rails back in that. I'll just go back since we only have 6 slides. Yeah, there's some rails back there. And you can see, so it just rolls off on there. So there's a couple of rails on both sides and wheels on the roof, and it rolls back. So yes, it's a roll-off roof. Okay, so basically we were just out of pure luck, we were able to upgrade and get a very nice, much nicer filter. I have to say that probably this is among the very best solar scopes in all of Indiana. This really is a very quality piece of equipment we have here. And for it to be sitting in the box for the last year and doing nothing, it was time to get it back. But there was a lot of work getting the new scope set up and pre-wired and all the things that go along with aligning it and getting all the new equipment put on it and all the software figured out and all that. So all that's basically done. So now it's time to put this guy back. And I was really driven hard to do it because of this social distancing, because I really want to bring this into the classroom now. And I think this is the way to do it. So anyways, the last slide here, and that's really what I wanted to talk about since I couldn't show you anything live. We're all solar system ambassadors here, basically. And what we do, we are assigned to certain states. So there's a number of ambassadors in each state, and they all vary. I think Indiana's got about 13 or 14 now. But we go out and do outreach for the Jet Propulsion Laboratory, NASA Jet Propulsion Laboratory. They team. We go out and we basically give presentations to schools, community groups, JPL, NASA, basically give us lots of materials to be able to provide to groups too. So we can bring out materials, we can put together presentations, we can do different kinds of organized activities. Just depends on the ambassador and what you want. Myself personally, I've always enjoyed talking more right in front of a telescope. So I always did my best work when I would work with some of the local children's museums and stuff, and basically just bring telescopes out there and show them the planets at night and stuff. It was always a lot of fun. I enjoyed it. They enjoyed it. That was the way I liked doing it most of all. I didn't like sitting in a classroom and just giving a talk or a brief like I'm doing now. So basically, that's what I thought. And after seeing all this social media, I thought this is the best way to get it in there. So as an ambassador and having this observatory, I'm basically going to mix the two together. Now, NASA's general purpose of having us, solar system ambassadors, are to basically give presentations and programs to sort of explain what's going on with NASA in terms of solar system exploration missions. So Mars probes, Venus probes, Mercury probes. There's a picture there of the solar probe. It's the Parker solar probe that's actually near the sun. All those missions, we get a lot of training and a lot of materials, and we're all generally very knowledgeable about those programs. So we can come and give briefs to your organization. So if you're a teacher, again, or an informal educator, or a community group, and you want to learn about something like this, call your social system, solar system ambassador, and we can put something together for you. And I want to highlight, again, we are really going to be, by the end of next month, those parts come Monday, we should have our solar scope back together and all tested out with all new cameras and everything within 30 days. So I'm looking to start live presenting the sun, not only for programs, but just in general. So on the Feynman Observatory Facebook page.
I think, Daniel, you'll have at least one 10-year-old named Zoe who will be very excited for that.
Sure.
She had some questions that Joyce, one of our other solar system ambassadors, has been answering in the questions for us because she's awesome. And I think Brian is ready to go with his target object. So if you're ready for us, I'm going to go ahead and pull back the host capability and hand that off to Brian and let him show off some space stuff.
Okay, great. Hey guys, welcome. I am coming to you from Sky Meadows Park in Northern Virginia. So my name is Brian Cummins. I'm an amateur astronomer. I live outside of Washington, D.C. In Fairfax, Virginia. And right now I'm in the middle of State Park. I'm doing the ultimate in social distancing because I think I'm the only person in the park right now. We have a good relationship with the park here. We do outreach activities with them. We do public nights for people to come out and look at our telescopes, see some of the images that we're showing. And in exchange for that volunteer work, they let us and give us 24/7 access to the park, which comes in handy. It was a little touch and go tonight with clouds, but I was able to snap an image to show you some of what we're looking at. And just to give you an idea, I am an amateur astronomer. I mentioned I'm not one of the professionals like some we have in this room. Let me share my screen. I can show you a copy of a picture of my rig and what I'm working with. Okay, can you see my screen, Amy? You're muted.
Yep, we can see your screen.
Okay, cool. All right, so this is
I bet you would have liked me to be off mute for that.
That's yes. Okay, that's all right. So this is a picture of the rig that I'm using tonight. The telescope is specially designed for imaging. It's an imaging Newtonian telescope. It's an old reflector design, aptly named after Newton. This red portion on the top, a little bit out of frame, is where the camera is. And I have terrible wire management, but all the wires are used to run the camera, run the focuser, and all goes back into this little tent that I have for my laptop that protects the laptop from the elements, but also makes it so that the light from the laptop doesn't disturb other folks who are busy doing astronomy. White light, which I'm shining right now on my face so you can see me, is usually not recommended at astronomy sites. People get sideways. So let me show you. What I picked tonight was the Rosette Nebula. The Rosette Nebula is an emission nebula. It's in the constellation Monoceros. And I'll show you, this is a planetarium app that I use to, it can be used to control the scope and aim at different targets. And I can click on different things and the telescope points to the object that I'm looking at. This object right now is very low on the horizon. It's actually a much better winter target. But I picked it because it's big, it's bright, it's easy to see, and I figured if I'm sharing my laptop screen, it'll be a lot easier for you to to see that. So this is where we're currently pointed in the sky. If you were out earlier tonight, you may have seen Venus, and several people recently have asked me what the big bright star is in the sky that they see in the evening. That is Venus, just in case you are checking. The Rosette Nebula is just a little bit, if you know where Orion is, it's just a little bit north and west of Orion, which by this time tonight has set. So this tells me right now this is where the telescope is set. It cleared off enough earlier that I was able to get an image. So the Rosette Nebula is an emission nebula. What that means is that the gas within the nebula actually emits its own light, which is a little bit different from reflection nebula, which is a nebula which it is reflecting the light of a nearby star. This type of nebula is actually emits its own light, which is charged by stars nearby. So this object is a popular object in the winter. It's about 5,000 light years from Earth, and is about 120 light years across. So it is a monster, and it is it's a stellar nursery. So this is where baby stars are born. So what I used for capturing this image earlier is what's called a narrowband filter. Many astronomy cameras are black and white because they're most sensitive. We get color images by using different filters and later putting those together, stacking up the images and putting them together using software to create a color image. As Amy mentioned, this is one exposure that was 300 seconds, and this is what a single exposure looks like. To make those pictures pretty, kind of like the ones you see in magazines, and one that I'll show you is sort of a completed image of this target that I've done previously. Typically requires, most people for good images takes 10 to 14 plus hours. I've seen people doing galaxies as much as 30 hours of exposure time. So these targets are imaged over multiple nights. We get what were called sub-exposures that we later put them together, again, using processing software and a lot of work to make these things look pretty. But this is kind of where it starts. It's one of my favorite images, and I can show you in my processing software where we would end up later. So that's my rig. I'll get rid of that. This is a finished version of the Rosette Nebula that I've done previously. And you can see this is a, excuse me, this is a color image. It is actually false color. It's using a special palette that's designed for narrowband filters. So it's not exactly what you would see if you could sort of see it naked eye. But it does give a really kind of cool representation of the gases, the stars, to really show some of the depth and the color that's out there in the galaxy. So that's Rosette Nebula, one of my favorites, and I thought I'd share that with you folks tonight. I think that's all I've got, Amy.
Brian,
Yes,
before
ma'am.
you're done, talk a little bit more about that, about the adding of the color to this, because we were looking at this image that you took, and it's that black and white image, which is stunning, right? It's stunning all on its own. And so I'd love for you to just sort of explain that a little bit more. I know how it works at the MMT, where we use our spectroscopy software, and it says, hey, this is what these gases are made of, and so this is the color, and it automatically puts it in. But talk to us a little bit more about the process that you go through. I think that's really cool.
Yeah, absolutely. So if I go back to this, and as you mentioned, this is what I get for a single exposure. This software allows me to use multiple filters. So the camera that I have has a filter wheel that is in front of the camera. I've got a combination of what's called broadband filters, which are used for sort of true color images. So when you think of the galaxy photo that you put up earlier, and that photo of the Orion Nebula you put up at the beginning of the presentation, those were taken with broadband filters, and is a pretty true representation of what it could potentially look like if you're looking at that with your eye. For emission nebula like this, as I mentioned, we use something called narrowband filters. What's great about narrowband is they filter out all the light except very specific wavelength of light. So it's great for filtering out light pollution when we're in light polluted areas, as many of us are, but also helps to just bring out the detail of specific type gases. This particular one that you're looking at is hydrogen alpha. So this is light that is emitted by ionized hydrogen gas. As I would image this particular image or this particular target, I would image in hydrogen alpha, in oxygen, and in sulfur gas. And that gives me 3 channels of monochrome images to work with. And if you know how images are put together in computer, it's with red, green, and blue, and those 3 channels come together to create a color image. So what's done here is I am mapping hydrogen alpha and what I get from sulfur and from oxygen into RG and B channels in something that is referred to as the Hubble palette. It's the comet made famous by the Hubble telescope, but it's a method of mapping those narrowband filter results into a color image to get you the final version of, you know, what I was showing here earlier. And then, you know, it's after that, it's a fair amount of work in this tool that this image is actually open in, that has a tremendous number of scripts, processes, tools to help bring out and adjust the image, to reduce noise. And there's a lot of noise in dim photos that you have to manage when you're imaging deep space objects like this. And so, you know, it takes a lot of work. And
Brian,
this is,
how
yes.
How long, we have a question from Sheila Freeman. How long did the stacking take?
So the stacking that the software goes through, you know, typically takes, it depends how much data that you're starting with, how many subs that you're starting with. The actual stacking routine that I use, which essentially takes all those images, aligns the stars to each other, and then puts all those images together into a stack where it's essentially producing an average of each pixel to give you a good image. That routine typically takes, depending on the data, 45 minutes to an hour. And then after that, it's, you know, a lot of work. I can show you, like, you know, oops, I guess I can't do it from here. I'm going up into a menu for Zoom. But in that process menu at the top, you would see a large list of processes that can be used to adjust the image, bring out brightness, bring out details, as I mentioned, to filter out noise that's common in deep space images. So, you know, the amount of time in post-processing after being out here in the field for usually multiple nights to collect all the data, you know, can be as long as, I have an image that I did of the Andromeda galaxy. That's one of my favorites. That one took probably 8 hours maybe of post-processing work, but that was a big image and required a lot of work. I would say this one, you know, probably took me, after the computer did all its stacking, for me to go through and make it work and make it look like this, took me probably about 45 minutes to an hour.
Well, that's amazing. And Brian, thank you so much for sharing the Rosette Nebula with us.
It's my pleasure.
It's great to have you here tonight. And
yeah, same here.
I know it's really late for you where you're at. We're actually gonna head over to the NSRO folks right now to let them show us the comet. I don't know if you're gonna stick around. If you do, please pipe up, you know, and help us
Amy,
out.
this is early for an astronomer. Come on.
Right now.
This is early for an astronomer.
And you know what? I call this late. I call this late because I would just be getting up right about now. I mean, I guess this is like really early.
I mean, it's 10:50. Come on.
I'm going to go ahead and get all those. Oh, yep. Thank you so much. All right. Let's see. So Shannon, I hope we're going to, we have a little problem there.
Okay.
So Shannon, we have a little bit of a problem since we don't have video for you. I'm not able to share to give you the host capabilities.
Oh, goodness.
Are you able to pause your video and share your screen?
Well, give me just one moment. Okay, I've enabled video, but there's nothing there.
So we're just, That's okay. So everyone, you're going to see a black screen for just a second while Shannon Morgan from the Mark Slade Remote Observatory gets ready to share her screen. So Shannon, what I'm going to do is I'm going to give you the host capability. I'm going to have if Jerry and everybody, if you guys want to maybe unmute so
Yeah,
that
we'll
you're
get-
able to talk.
We'll
So
get
everyone
Jerry
from-
and
go
Myron
ahead and
unmuted.
unmute, and then I'm going to give Shannon. Yeah, Myron and Jerry. So it looks like we're just waiting for Myron to unmute. He's on the phone. And
Yep.
Shannon, I'm going to pass the host capabilities to you, so you can show everybody Comet apps.
All right.
Does Myron know how to do the keypad to unmute his phone?
I did send that to him, but I'm not sure if Myron, it's *6 or perhaps just 6.
Shannon, I believe as the host now, you can force unmute.
How's
him.
that? Can you guys hear me now?
There we go.
Got me?
Yep.
All right. I can hear you guys. If you can hear me, we're good.
Okay, excellent. So I hope you can see on my screen a picture of Comet Atlas that Myron was able to take just a few minutes ago. Unfortunately, in the past probably 10 or 15 minutes, Comet Atlas has moved down below the tree line for us. So this image is not old. I believe it's a stacked image of 5 images. We took the last 5, Myron took the last 5 images and then put them together, stacked them to make an image. But this is, how old is this image, Myron?
This image was taken about 10:30 this evening Eastern time, so about 7:30 Pacific.
Okay. All right. Well, so there are 3 of us here from the Mark Slade Remote Observatory located in Wilderness, Virginia. It's an incredible observatory. One of the most interesting capabilities it has is, for example, I am in Durham, North Carolina, but I can log on to the telescope computers and control pretty much every facet of the telescope as if I were sitting right there. For one of them, I can open the dome, I can power up all of the cameras and use it just as if I were sitting there. For some of the other telescopes, we have Myron to help us with the rolling off the roof or pushing the shed out of the way, whatever is needed at that point. But Myron has been imaging Atlas since, I believe, April 3rd.
Yes,
Is
April
that right?
April 3rd was the first night. Correct, April 3rd.
Okay, and
Mhm.
if you give me one moment here, I will see if I can show you a video that I put together. These are very raw images. They haven't been tweaked with to look pretty, but I wanted you to see how Atlas has been changing from April 3rd until last night, I believe, is how long my video image goes. So I'll see if I can start this. And as you'll have to forgive me, I'm kind of new with Zoom and I'm not quite sure how to change it from looking at the telescope view to looking at the animation.
We can see it over
Oh,
top
you can
of
see
the,
it?
yes.
Okay. Okay, perfect. Okay, so this is, and you can see satellites going by. This is quite, I believe it's 1,100 images went into making this animation. And you can see just how quickly it's moving against the background stars.
And as well as the changes in the physical makeup of the comet itself on the images changes noticeably during the sequence, as we've been fortunate enough to actually be able to observe this comet as it's disintegrating. Normally, these kind of comets, when they are this far from the sun, are fairly stable in terms of their appearances. They don't break up before our eyes. But Atlas is different. Atlas is we think, a fragment of a great sun-grazing comet called the Comet of 1844, perhaps broke off thousands of years ago, and is now just making its way around the solar system into the inner solar system. And due to the heat and light and gravitational pull of the sun, it's breaking the comet up before our eyes. And I've been fortunate enough to have a really, really unusually clear spell of weather here in Virginia. Over the past couple of weeks, I've gotten an image of it almost every night. So I've been able to document the comet's appearance from early on when it was a very condensed, very bright nucleus with a nice round diffuse coma around it and a very, very faint tail, to multiple fragments breaking off of the nucleus and creating their own disturbances and changes in the appearance of the comet in the tail. And indeed, on one night, on the night of April 20th, was actually able to image the comet with a double nucleus, actually. It looked like two eyes looking back at us. And we'll share that image with you in just a little bit. But
I had another image that I wanted to pull up. One of the most interesting images that Myron captured was on, let's see if I can read the date here, on April 17th. While he was imaging the comet, it's kind of faint here in this image, but the vertical bright streaks are from the Starlink trails from the Starlink cluster of Starlink satellites. That's how many really bright satellites went through all in a group through this image at the same time, which can present challenges when you're trying to do scientific imaging. You don't want satellites going through your images. So it's going to be interesting to see how this shakes out with all the Starlink satellites that they're planning to launch, how much this will actually affect our viewing. But here we go. We got it in this one image.
Yeah,
Myron,
and
I just had to show that.
That's fine. That is. I think it's an interesting image to look at too. When I first saw that, I didn't really know what it was at first. It was so bizarre. Then I realized it had to be the Starlink satellites because there were so many of them traveling in very, very close orbits, almost the same orbit. You can see there's a little bit of displacement between the trails, but they're pretty close together. Our field of view in these images is not much. It's less than the diameter of the moon in the sky. So these fields of view that you're seeing are fairly narrow. But the comet has been very unpredictable. Every time I think that it's going to die, and I slew the telescope to its position in the sky, I half expect it to be gone because the nucleus is broken up a number of times during the sequence of observations that I've been doing, and yet every time I look at it in the telescope, in the image, there it is. It pops back into the view. So it's a little comet that could, I call it. It just doesn't want to die, and it's just interesting as tonight's image shows that it has a very nice, bright, relatively bright, condensed nucleus. So there's still a bit of life left in this comet. It's still about a month away from its closest approach to the sun. So it's got a ways to go. And comets are notoriously unpredictable objects. The person that thinks they know what's going to happen is fooling him or herself because we just really don't know what's in store with this comet.
Yeah.
I've seen it fade out and fade back and thinking, okay, this is it. And then I look at it and it's bright again, relatively speaking. It's healthy, relatively speaking, for itself. And then the next night it looks very, very ghostly and pale. And then I'm thinking, okay, this is it. And then the next night it's got two nucleuses. So it's unpredictable. We just don't know what's going on. But it's been a really fun comet to observe, and it's not really easy to see visually. You can't see it with your eye. You can't even see it with binoculars right now. And even with the telescope, it's pretty hard to see because it is so diffuse and faint. These images were taken that you're looking at least the pseudo live one that we have here was taken with a 12-inch telescope. So it's a pretty good sized telescope. And that's why we're able to see the comet as well as we can. But it is a difficult object to see right now.
Myron, could you pull up maybe two
Yes.
of the images that you processed that show the nucleus when it was compact and then the nucleus
Absolutely.
when it was in two pieces? Because those are fantastic. And if you could make them perhaps fill the screen, I think
Okay.
people would like the biggest image we can get.
All right. Okay. So here's a picture.
Could you zoom in on that?
Yes,
The
I
plus
can.
there? Perfect.
Good. So this is an image of the comet that was taken with one of our, we have 3 stations here at MSRO, Mark Slade Remote Observatory, 3 stations. This was taken with station 3, it's our newest one, which uses a 102 millimeter, that's a 4-inch apochromatic refractor made by Explore Scientific. And it shows if you can see my mouse cursor here, the nucleus of the comet. And this is a stack of 100 images that were each a minute long. So this is 100 minutes of the comet's motion in the sky stacked on the comet. So the stars look like these trails, but the comet itself is centered and appears the way that it would if you were able to track it with the telescope. And what you can see is there's a faint little, yes.
I'm sorry,
I'm sorry.
Amy, we have two questions. So I'll give them to you and then you can answer them when you're able. So we have
Sure.
a question from Pamela Hoffman. What is this comet comprised of? And then we have a follow-up question from Nick Koch, which is what would cause the nucleus of the comet to break up?
Great questions. Yeah. So in 1950, we really didn't know what comets were, but a very forward-thinking astronomer, Fred Whipple, came up with a theory and published a paper about what a comet really was.
Why, thank you.
Yes, and he came up with the idea that comets were basically dirty snowballs. So they're not very big. The nucleus of the comet you cannot see when you're looking at it in a telescope like this. What you're seeing is the dust and the gas evaporating off of the nucleus of the comet as a result of the warmth of the sunlight evaporating the water. So a comet is basically an object that's the nucleus is maybe about 10 miles in diameter or less in most cases. But because it's made up of ice and dust, as well as some carbonate materials, carbon dust and stuff, it actually, the water evaporates and sublimates into space and creates this glowing cloud of dust and gas around the nucleus. So you don't actually see the nucleus, but what you see is the glowing cloud of gas and dust around it. And it's a small object, and it's not really held together very strongly because, the bigger an object is, the more it's held together by gravity. The bigger an object is, the more mass it has, and the stronger its gravitational pull is, so it holds together better. Well, these comets are very small objects, relatively speaking, and they have a very, very weak gravitational field. So the material that makes up the comet is very loosely bound. And so when it gets close to the sun, the actual forces of the sublimation process of the gases and the dust coming off the surface of the comet produce kind of like a sandblasting effect, which can actually help disrupt the nucleus itself and break it up into fragments. And then they can actually float away from the main body of the comet into space around it. And because they're made up of the same material of the comet, they become sort of their own little mini comets around the nucleus of the main comet. And you can see that in this image as a very faint little dot right near to the left of the center of the comet. And I want to show you another one. The other thing that can disrupt comets is the pull of the gravitational field of the sun as well. And as they get closer to the sun, that gravitational field gets stronger and it can disrupt the nucleus of the comet. This was taken with the same telescope, the 4-inch Explorer Scientific Apo refractor, on the evening of April 15th, when there was a very clear disruption going on. Look at the comet. It doesn't even look straight. It's got this kind of a J-shaped hook to it here. And the main nucleus of the comet right here, you can see is kind of oval and aimed up at an angle. And then there's a condensation in the dust tail itself that obviously is basically a concentration of increased dust and gas.
Can you zoom up even further, make that a larger, full screen?
Yeah, again, indicating that it is basically being torn apart by the pressure of the sun and light and the gravitational pull of the sun itself. So I was getting really excited when I was giving it. I saw this happening. It's like, wow, this is really cool. The comet's breaking up before my eyes. And then this was just a prelude of the things to come. The most spectacular night was the night of the 20th of April, when I obtained this image here. Now, this was taken with our Station 2 telescope, which is 12-inch. I was able to employ both telescopes observing the comet at the same time that night. And look at that. The nucleus actually was double on this night. I saw that as like the first time in my life, and I've been looking at the stars for more than a few years, and I've never seen anything like that. And that was to me was an amazing sight. And we got a really cool animation I made that night when I saw that of the comet. I could show that if you guys would like to see that. I don't know how well it'll play over the with the Wi-Fi I've got going here, but what I'll do is I'll just kind of get an idea of what this image looks like right here. This is a stack of 50 30-second exposures, and again, that's why the stars look like streaks and the comet is. I stacked the pictures on the comet so it looks like it's not moving and the stars are, but it's really the other way around. And so what I did is I took these 50 exposures and I ran them in a loop and I created this animation. Let me show you that right here. And this animation, I think, is really, really kind of cool. I don't know how well this is going to look, but let's give it a try here. Okay, here we go. This is the same night. This is all images stacked together, and they show the motion of the comet over that time period. And you can kind of see, if you're lucky and you have a little bit of imagination, the two concentrations in the nucleus, the double nucleus as it's moving there. Okay.
Oh, it's showing up pretty well, I think.
Did it show real? I'll run it again one more time if you'd like, just to, because you can see the two nuclear components right there. And this was taken just what, on the night of the 20th, our local time. So, and then I did one more thing. I went ahead and I looked at it again the night after, 24 hours later. So from this picture that you see in the bottom here, 24 hours later, I re-imaged the comet to see if maybe we would have two comets with each having its own nucleus, or whether we'd have more fragments appearing. And guess what we had? Here's what we had. This is a little tricky to watch. I've stacked on the comet itself. This is 2 nights. You can see the nucleus of the comet and the 2 fragments right there. And then the one just disappears. So the next night, 24 hours later, we're back to a comet with just 1 nucleus. So the one that had broken off had completely disrupted and faded away just almost into obscurity. So again, no double comet, but still very interesting nonetheless, I think here. So again, just shows we just don't really know what this comet is going to do for us. Okay, and these are, I'm just going to run some loops that I've created over the past few weeks that show the comet changing as it's passing. This is all taken with the 4-inch telescope in station 3, which is the 102 millimeter refractor. And notice how the comet's getting dimmer. It looks, the bright concentration of the nucleus is fading. It's getting dimmer. It's spreading out. Now you can actually maybe even see some fragments in the comet as it's orbiting. And there the comet is getting more spread out, more diffuse. And in this next image, right here, you can actually see a large fragment preceding the comet offset from the comet itself, giving it that sort of that J-shaped look. And that was the night of the 13th there. Okay, well,
it's been an exciting comet.
It really has, for being a small, almost invisible comet. For
we've got a couple of questions.
Sure.
Here, if you don't mind, Myron. If you know, Chris Rappel asked, how long is the comet's tail in these pictures, if you know? And then we have a question from Nikki Hockaday, which is what happens after the nucleus splits?
Okay, so the first question is hard to answer because it's hard to tell where the tail actually ends because it's a very diffuse kind of a feature. But typically comet tails can be hundreds of thousands to millions of miles long. And in some cases, in the case of like the really, really bright comets that you can see with your naked eye, those tails can stretch tens or even hundreds of millions of miles. In fact, just to give you an idea, in 1910, when Halley's Comet was passing by the Earth's vicinity, the geometry of the comet and the Earth were such that the Earth actually passed through the tail of Halley's Comet. And people were in a panic because scientists had just discovered that some poisonous gases were actually present using spectroscopes. There was poisonous gases like cyanide in the tail of the comet. And people thought, oh my gosh, if we're going to pass through the tail of the comet, we're going to have this this poisonous gas in our atmosphere. We better protect ourselves. So people were closing their windows and shutting up their houses and sealing them with plastic and buying gas masks. And there was panic, and it was quite an experience. Comets are notorious for bringing ill omens in the past. They were perceived as being omens of poor portent. They were not good things to be seeing in the sky, because usually bad things were predicted to happen when comets appeared. But comets are very beautiful, and they're ephemeral, and they're different, every one. There's no two that ever look the same, even through a telescope. Every one is different, just like your fingerprints. Everyone is different, and you never know what they're going to do. That's why that makes them exciting. So the second question is what makes the nucleus break up? Was that correct, Amy? I'm sorry.
Well, I'm sorry, Myron. So the question's been clarified. It is, has there ever been a new comet created after the nucleus split?
You know what? There have. There has been a number of comets in the past that have fragmented to the point where you actually did see a number of smaller comets orbiting the sun in the same vicinity. And I think one particular one that I might be mistaken on, but for some reason the name sticks in my mind, is Biela's comet, B-I-E-L-A. It actually split into several components, and there are photographs that exist that show the multiple fragments with their own individual tails. Now, on this comet right here, if you have a powerful enough telescope, like for instance the Hubble Space Telescope, you can look at it and you can see the multiple fragments looking like individual comets. And I would encourage everybody here, probably you've seen this image. It's a beautiful image. It was taken by Hubble Space Telescope. You can Google it. It shows the breakup of the nucleus of Atlas, and there's 4 components. And there's 2 components that are close together, and another 2 components that are close together. And those 2 separate components, each containing 2 fragments, are what we're seeing here in this image. This image is actually, even though it looks like only 2, there's actually 4 separate fragments there. 2 of them, each cluster is too close together for the 12-inch telescope to resolve. So you can't see the individual 4. You can only see the 2 groups of 2. However, if you look at Hubble Space Telescope's image, it was taken at about the same time this image was. You can clearly see there's 4 major fragments and a number of smaller ones. It's a really cool image. I wish I could bring it up, but I can't on my screen right now.
I almost went to go search for it, and then I remembered, no, I'm sharing my desktop.
Yeah.
So I can't look for it at the moment. But one of the most fascinating things about comets is what they're made of with their dirty snowball consistency. They are the primordial elements that our solar system was formed from. So like after the sun formed, there was all this ice and gas and dust and rocky material out there that coalesced to form planets, asteroids. But the comets are unique because some of them are so far away from the sun. The Oort cloud, which is where most comets originate from, it's about a light year from the sun. It's this belt that goes around the outside of our solar system. And comets can have orbital periods of 1 million years. We might have a comet come by that will never come by again because it gets flung out of our solar system, or it gets into this very long orbit where we won't see it again for 1 million years. But the composition of them is so fascinating. It tells us what was here before planets were formed. And the European Space Agency spearheaded a mission that NASA participated in to a comet. You may have heard of the Rosetta mission. And they actually tried to land on a comet, which they were successful at landing on it, but then the little lander kind of tipped over in a shadowed area of the comet, and unfortunately it ran out of power. But you can Google the Rosetta mission and see just some spectacular images of this lander coming up on the comet and the comet getting bigger and bigger. It's really quite fascinating. But to wrap up our little segment, I would love to turn this over to Jerry so that he can tell you a little bit about MSRO, which I'm going to pull up our website up on the screen. And actually, I'm going to pull up our links first. So if you ever want to find us, you can go to msroscience.org or on Facebook, facebook.com/msroscience. And Jerry, I'll let you tell everyone about what we're about.
Yeah, so Myron actually started back in 2015. We formed the MSRO's commission to build the first observatory, Station 1. And I work for Explore Scientific, and was fortunate enough to be able to help provide equipment for our observatory. And so that's how I got involved with Myron. Also, I'm into remote observatories, and so this was the first one I was involved with Myron. The Mark Slade Remote Observatory is named after an amateur astronomer, astrophotographer, an excellent friend of Myron's for a long time, Mark Slade, who passed away in 2015, and a big chunk of equipment was left to Myron to build the observatory. So I got involved since I know a lot about the computer systems and the control systems and build equipment and stuff like that. So I got involved with that. But we provide we have 3 stations, like Myron said. The main one has a 6.5-inch refractor as the main instrument. The second one is a 12-inch Meade system, and with fork mount. And then also we have the 4-inch system that we recently just put in service. So if you to find out more information, go to msroscience.org, and you can find out all we do. We're a nonprofit we're into outreach, training, and research.
Oh, I had myself muted for a moment, but thank you so much for letting
so
us be a
much,
part of
everybody,
this.
from
This is
the-
wonderful. And I'm going to see if I can figure out
Thank you guys
how
so
to,
much for being here.
I've got to figure out how to pass the
Sure.
meeting control back over to you.
Oh, it's okay. I took it from you.
Oh,
I
excellent.
took
Excellent.
it away from you, and I'm passing it over to Mike Keith. So I'm announcing that to Mike, hoping he's hearing me.
Yep. Yes, I am.
Okay. All right. So Mike, I've passed you the baton.
Fantastic.
And if
Thank
you don't
you.
mind, if you'll a little bit about you, an astro nerd, while you're setting up your screen there, I think that everybody would be very interested to hear.
Yep, absolutely. Just trying to get it to accept, and then hold on, just gonna hit share. Okay, so hopefully my screen comes up. And it's telling me I am sharing. So if someone just can confirm that you're seeing my screen with a nice galaxy.
I can
up on there.
confirm.
Yes.
I see your galaxy.
Yep,
Fantastic.
we see it. M51.
Yep. So my name is Mike Keefe. I like to refer to myself as the Astro Nerd. I am a amateur astronomer, as well as one of the solar system ambassadors, like my colleagues here. I am located in Apex, North Carolina, which is right outside of Raleigh, and we have been battling clouds all night long, as well as some equipment issues. So about 10 minutes ago, my telescope stopped responding. So luckily enough, I had a few things captured here. So what I'm doing in this scenario is similar to what you heard Brian talk about in terms of kind of amateurs using cameras to try and capture data and then obviously display this data in terms of pictures. But what I do differently is something called EAA, which stands for Electronically Assisted Astronomy, which is a fancy way of just saying, instead of using the typical eyepiece and staring through that eyepiece, I'm using a camera and then displaying the data from the camera live onto the screen. And where oftentimes astrophotographers will try to capture as much data, and you heard stories about taking hours and hours and hours of data, and then post-processing them. The goal of EAA is to really get enough data so you can see the image that is more enhanced than you would if you were just looking at it through an eyepiece. So unfortunately, like I said, I've lost connection through my telescope. And what you may see on what I'm sharing on the screen is that I get this warning that frames are being dropped and can't stack. So we're using very similar technology that astrophotographers use to, in essence, stack frame upon frame upon frame. Like I said, unfortunately, my telescope is not responding, so it's now not looking at the galaxy. I can show you exactly what it's staring at right now. And that is a view of what it's staring at, just stars kind of crossing through the view. But I wanted to share with you this particular stack that I had. This is 5 images of approximately 15 seconds each, which gives us a 75-second total exposure of M51 called the Whirlpool Galaxy. And this galaxy is approximately 23 million light years away from us. It is interacting with this smaller dwarf galaxy, sometimes called M51b. This larger one is called M51a. It also goes by the designation NGC 5195, I believe. But that's part of what they call the NGCs are called the New General Catalog. And what I really enjoy about EAA is when you use a program like I'm using, I can start to stretch the histogram, and I can play around with the saturation, the kind of the colors, to try and really tease out detail. So I can do something like this. So I've done an auto stretch. You heard some other people talk about getting a lot of noise when you're doing these deep sky exposures. This is a perfect example. You can kind of see this graininess in the background. That is noise. In fact, most of the time that would be processed out in all the different steps you take afterwards. But obviously with EAA, that's not something you're doing. But I occasionally like to kind of overexpose or kind of oversaturate this with the histogram because you can really start to see some of the structure of this galaxy. This is a face-on spiral, and you can really start to see these spiral arms. You can see some of the dust there, and this is a beautiful dust lane that is going from M51, and you can kind of see it stretching out over to the location of the dwarf galaxy. So it's a great way to be able to do observing with the kind of using some of the technology, but not having to necessarily spend so much extra time processing. These pictures aren't going to win any awards. They're not going to be published in any magazines. You'd have to really spend a lot of time enhancing them, but it is a way to really try and get some good views. I'm just a few miles outside of the city of Raleigh, so we have some fairly light polluted skies here. So this is a great way to help combat light pollution. So that is M51. I'm going to switch over to, I did take a few other pictures and I saved them. These were some other pictures. Go ahead.
Actually, Mike, you said something. You said something that leads right in for me to actually talk about Dark Skies Week, if you don't mind.
Absolutely.
While you're kind of pulling up some of your pictures, I'm going to talk about Dark Skies Week for just a second here.
Certainly.
All right, I'm going to read that. Everybody, look, we're getting better at this. Everybody, And then, let's see, I've reclaimed the host. Oh, there we go. Look, I can share again. Okay. Everybody, actually, I think so the funny thing is I think you've all been looking at the side of my face all night. Okay. International Dark Skies Week is April 19th through the 26th. So we're just coming up on the end of International Dark Skies Week. If you guys don't know what that is, it's a celebration of our dark skies. And it's also a time for us to really reflect on changes that we can make and what's really going on in the world. So I'm going to show you a couple of things. Up on the screen, you should see John or Jerry, if you want to wave at me so I know for sure that people are seeing what I want them to see. Thank you, perfect. What you're seeing right now is a map from 2016, actually, of lights. So this is Earth at night. And the really interesting thing is that, you know, in 2016, the statistic was that more than 80% of Americans alone, if you look at the United States of America here, you will understand this. More than 80% of Americans could no longer see the Milky Way. They could not walk out of their home and see the Milky Way. I'm very lucky because I can see the Milky Way. If I walked out of my house right now and turned out all the lights and stayed outside and did the dark adaptation I told you about at the beginning for 10 or 20 minutes, I would, you know, keep my eyes closed in the dark, look up, and wow, there it would be. And John, you know, lives in a pretty similar place. Brian's out in a similar dark place. Mike's out in a similar dark skies place, and we're very lucky to still have these spaces. We have something here in Arizona called the International Dark Sky Association. We're very lucky to have these individuals here close to us, but they work on an international scale, helping to not only protect the dark sky areas that we have left. You can see, you know, places like if you look over at the United States there, you can see there's still some dark spaces, and they're working to retain those. If you look at Africa, a lot of Australia, a lot of South America, there's still dark spaces there. And we're really working to preserve the night, but also to reclaim some of that by educating people about light pollution and about the really simple changes that you can make. Now, if everyone in the entire world just went out outside, shut out all of the lights on their homes, shut out all of the lights on their businesses, we shut out the lights at mines, we shut out the lights at airports, this is what the night sky would look like. And if you have never seen the Milky Way, I'm going to be really honest with you guys and tell you I'd never seen the Milky Way like this picture until 2018. It's 2020. I am an astronomer. And, you know, I mean, my primary job is science communication, but I work in astronomy, and I've hitched my wagon to that star, so to speak, for a very long time. And just 2 years ago, I saw the Milky Way like this image. But if we all helped to turn out the lights and to re-celebrate the dark and our connection to the night sky, this is what we would see. It's really phenomenal. Now, I'm going to show you this little animation from our observatory, Mount Hopkins in Amado, Arizona. It's okay if you've never heard of that place, you can Google it later. It's in the middle of nowhere. In 1968, on the Bortle scale, we were a 1. The Bortle scale is the light pollution scale. You can see what our Milky Way would have looked like to us at our observatory. Right now in 2020, we're a 3. The scale goes to 9, by the way. So you can see we've lost a lot of that definition and our ability to see, because light pollution blocks our ability to see into the night. And of course, by 2025, we're expected to be a 5. And look at that difference. Look at that change. And I'm sorry, my internet connection is being unstable. I also live in the middle of nowhere. But so you can see that change that is happening. If you live somewhere like Phoenix, Minneapolis, Detroit, Michigan, and if you live in Michigan and you're out there and you've been to Detroit, kind of know what I'm talking about. You're standing in the middle of Detroit and you're not seeing the stars. If we're in New York City or Los Angeles, they're working very hard to cut light pollution, but we're still going to face those problems. And so I want to talk to you about what it means to make a simple change. All you have to do is turn the lights out on the outside of your house at night. That's the biggest and simplest change that you can make. If you want to make a really permanent change at home, you can change your light fixtures. The light that just shines out and has no cover is the worst. If we have a semi cut off, but a lot of it is getting up into the night sky, that's still bad. Good is a lot of cutoff, and better means all of the light is going down to the ground. That's where we want it anyway, right? I mean, if you're walking outside in the dark, you don't want the light above you, you want it below you. You want to be able to see where your feet are going. And so it's really important to think in those terms. And also I want to encourage you to sometime, at some point, look out into the distance and see sky glow. From here, from Rio Rico and Amado, Arizona, I can see Tucson more than an hour away. I'm sorry, there's a bug flying around in my house. It's very distracting. But I can see those lights. I can see what's called a dome of lights. And that's sky glow, and that blocks our ability to see into the night. But light pollution also disrupts bird migration. It disrupts those baby turtles that you love so much that are swimming up onto the beaches innocently and are in the danger zone in Ecuador. It confuses whales. It messes with your body chemistry. It messes with your sleep. It even messes with your growth. So if you're young out there, we've got a 10-year-old, Zoe, we've got you out there. We've got one of our Girl Scouts out there. It's messing with your sleep. And so again, this is a time to reflect on the night, reflect on dark skies. And we're going to actually go back to Mike now that he's had a chance to get another really wonderful image up for you. And I want you to think about how much more beautiful our images could become looking through these telescopes and what we could all see together tonight. If we all just turned out the lights. All right, Mike, you are the host.
Okay. Let me see. Try sharing again. Apologies. Okay, so I will also make a ploy there or a pitch on the dark skies. And this unfortunately is a view where that my orientation is actually towards looking over where Raleigh is, and I do have a lot of light pollution coming through the image that I was taking. So yeah, it does absolutely disrupt the astrophotographer or the astronomer's ability to get data. But I think it also has a huge impact on society as a whole. It costs more. It costs more to light up and light out everything instead of focusing it down on the ground. And it causes glare. So it actually can cause some safety issues where you really can't see very well. So again, just a few other points. So these images, so everything I'm showing you was literally taken between about 10:30 and about 11 o'clock. They were just different views that I was able to snap. Again, this is still stuck. I have to run through a different alignment routine, but this is basically near real time. It's as live as you can get showing this. And I think that's really just kind of blows me away when I think about it, that we're staring at a galaxy whose light has taken 25 million years to cross intergalactic space to this evening, bounce around the inside of my telescope, hit the camera detector, and then obviously display this image for us. So 25 million years in the making, and it's literally what we saw. In this case, it was about I think 11:05 was the last time I was actually able to get a particular view. So again, it's amazing what we can do with technology these days. If anyone is familiar with certain telescope mounts, mine is a fairly simple mount. It's called an alt azimuth mount, meaning it doesn't actually have to be aligned with the same rotation of the Earth. And the software these days, and you can almost see it in some of these pictures, the software itself will align on the various stars and rotate the image, so we don't get streaking in these views. And you can see the fact that you can almost, if you look at the edges here, you can see how we've had in this case, this is 27 different stacks. They've started to kind of turn and turn and turn, and that's this effect you get at the edge. So it's a great way to get started into astrophotography if that's something that people want to do. But it's also a great way to enhance just your observing. So I just wanted to share just a few of those live views, and again, it just different ways of stretching the actual image, and you can see how that affects the outcome depending upon what we have in the background sky. And then again, this is another just a view where these are just screenshots of what I took. A lot of noise in this scenario. So I guess I'll pause and there and hand it over to whoever has got the next object.
All right, thank you so much, Mike. Yes, so I will, well, maybe I'll attempt to take it from you unless I have it. I don't think I have it back. I don't know what happened. There we go. We will hand it over to John, and I'll introduce John very briefly, and then let him talk about himself for just a minute and the Prescott Astronomy Club. John has been an amateur astronomer. As well, not see my face. John has been an amateur astronomer since 1986. He'll correct me if I'm wrong. And he is also the president of the Prescott Club in Prescott, Arizona. So John, I'm going to hand over the hosting to you and let's get started.
All right, thank you very much. Let me see if I can get my screen started here. Yes, I can. So I want to go to desktop 2. And what you're seeing right now is my observatory that I built out of my own 2 hands, almost. What we have here is a 12-inch or 12-foot long by 10-foot wide metal shed. I just went down to Lowe's and picked up this metal shed, and I just detached the roof from it. And I put it on garage door rails so it slides completely off. And inside here we have a 14-inch Celestron telescope. It's called the Edge HD, which is supposed to be a pretty good quality telescope. And sitting on top of that in piggyback is a 4-inch refractor from Stellar View. And you'll notice out here on the end, I've got a camera, and tonight that camera is non-functional. But it worked last night, and I got some pretty good pictures last night. On the end of this one, I've got a DSLR. It's a Canon 6D, and it's modified and cooled, so it takes really good pictures through here. I've got some images of that as well. Now I can also take that camera off the front. It's actually attached to what is called a hyperstar lens. So we take the front off of, there's a mirror generally right there on the front of the telescope. So we take that mirror off and attach this hyperstar lens and then attach the camera to it. Well, I can remove all of that and take that camera and put it on the back end, and I can attach it to the back end, which is where people would normally expect to see either an eyepiece or a camera. So this is how I can configure it. It can go one way or the other. I've had some pretty bad success with cameras lately. 3 of my cameras have been in and out of the shop over the past year, and I'm not quite sure why this is failing on me right now, and I've got some ideas, but let's not go there. So the next image that I want to show you is a little closer look up, close-up of the telescope itself. So here we see these are 22-pound weights on the end of this shaft. And I've had to put an 8 or 10-inch extension on this so that I can get enough weight down at the end to carry what I put up here. And it works pretty good. I'm enjoying it. So you can see here I've got the roof actually clamped down so it doesn't blow off if there's a high wind. It works really good. Excuse me. The next image is another view of the telescope. So this is the close-up of the telescope showing you the different cameras. This camera right here is my guide scope camera, and it's a Meade DSI-2 color camera. So I'm taking pictures with this to enable me to track the telescope. So the images that come off of here go into my computer and then feeds back to the telescope to keep it tracking with the stars. This apparatus that you see right here is called a TELRAD. It's a finder scope or a finder. You look through it from the backside toward this area and you'll see 3 concentric red circles in there. When the star is centered in those red circles, then you'll know that whatever you're looking at here is going to be on that object. So that's what the finder scope is for. Moving on to the next image, I'm going to show you what my control room looks like. I've got 2 27-inch monitors. They're identical. This is my Apple computer that drives everything. It actually is running Windows operating system as well. A lot of the software that we use for astronomy is actually more suited for Windows, and some of it is actually working for the Mac, and as soon as everything gets working for the Mac, I'm going to give up Windows. So now I'm going to show you some pictures that I have taken in the past. This is called the Dumbbell Nebula. And actually this is a fairly recent picture, but you'll notice a lot of speckling in here. This is noise. The noise can be filtered out, but again, with electronically assisted astronomy, you really don't go to all the trouble of filtering out the noise because you literally take one picture and that's it. So there's another group of people that say, look, only want to take one picture. So they use a DSLR camera, they snap a single picture, no processing, and they put it on out there for people to look at. This is called the Cocoon Nebula. So the Cocoon Nebula is what we call a gaseous nebula. So this is gas that's literally possibly formed either around this star or that star has shed some of its gases and it's radiating outward. There's also a lot of dark area in here. That's still gas, but it's so dense that light can't get through it. So that's what that's amount to. The next image that I want to show you here is M2, Messier 2. Now the reason, I'm going to tell you a little story about Messier. French astronomer back in the early mid-1700s. He was more fascinated about comets than anything else. He thought comets were the bee's G's. So what he did, he was hired by the French government to look for comets because they believed that a comet, the appearance of a comet, meant the death of a king. That was one of the things that they were into those days. Well, the comet never showed up. The king died anyway. But one of the things that Messier wanted to be known for as an astronomer was to be the first astronomer in his era to see Halley's Comet when it came by. So he was busy out there with his telescope pointing here and pointing there and looking for any instance of the Halley's Comet. And his wife was noticing and she tapped him on the shoulder and said, "What's this over here?" She could see Halley's Comet with her eyes before he could find it with his telescope. Now that's what we call tunnel vision, or telescope vision in this case. So that's a story about Messier. So this next one here,
Hey, John, I'm sorry, I'm going to interrupt you for a second. We have 2 children, Justin and Addison, aged 7, who would like to know how you got started in astronomy.
Oh, that is it's a heartwarming
It's actually
story
for
me.
everybody. So
Sure.
after John, everybody can.
Yeah. So I'm 80 years old now, just for the heck of it, so that you know. In 1986, I was working at a place, and one of my friends that I was working with, he happened to tell me that he was grinding a mirror to put into a telescope. And I go, why would you grind a mirror? You just go out and buy one. And he goes, no, it's more fun to take a piece of glass that's 1.5 to 2 inches thick and rub it and rub it and rub it until it's got a concave shape to it. And then you put aluminum foil on it. You know, literally it's a deposit, not an aluminum foil like you get out of the package. But you put a layer of aluminum on that and it becomes a mirror. And then you install that into a tube. And I've still got that tube, by the way. So I asked him what he was going to do with it after he was all done. He said, well, I'm working, this is a 10-inch mirror that I'm working on now, and my next one is going to be a 12-inch mirror. So I said, well, what are you going to do with this 10-inch mirror? And he said, I don't know. I never thought about it. I just put them aside and go to the next one. So I said, well, how about I buy it from you and I put together a telescope and it'll be my first, because I was just curious about astronomy. So he says, okay, I'll tell you what, I'll put it together for you. I'll build the telescope and I'll sell it to you. But I don't know how much yet. So about 2 weeks later, he comes back and he says, how about $600? And I had no idea how much a telescope was worth, but I had $600. So I gave him the $600. He gave me a telescope. And I've still got that telescope in my garage. And it's a fantastic telescope. It works really well. And it has another story associated with the mirror. After you grind the mirror, and before you put an aluminum deposit on it, you have to do what they call configure the mirror. And configuring the mirror means checking to see if a straight line across the image at any point doesn't bend. So there's this guy up in San Francisco called Dobson, Dr. Dobson. He was a priest, and he basically gave up the priesthood so he could start the San Francisco Star Party, or what they call the Sidewalk Star Party. And I took it to him, and he took it outside, and I was watching him, and he looked it up, and he was having there was a telephone pole about a block away, and he was moving the mirror back and forth in his hand, and he handed it back to me, and he says, I don't see any problem with this. And I go, that's fantastic. Usually there's something wrong that you have to go back in and grind out to get a little bubble out or a depression and reconfigure the mirror. So I went and had it mirrored, had an aluminum coating put on it, and stuck it in that telescope, and it's still getting really, really good images to this day. So I'm really pleased that in 1986, a friend of mine just got me interested in astronomy because he mentioned it to me. So now I mention it to you guys. One of the ways that you can get started in astronomy is don't buy a telescope. Join the local astronomy club in your city and use their telescopes. That's the best way to get started. Or their binoculars. They have star parties every now and then, public star parties. And if you ever get the opportunity to go to the Grand Canyon every year, and it was going to happen in June of this year, every year they have a public star party where thousands of people go, and we show our telescopes, put them up in the night sky, and let people look through eyepieces and look through cameras and show them things they have never seen before. It's really exciting. So yes, join your local astronomy club. I'm the president of the Prescott Astronomy Club in Arizona, and been with them since 2006 or 2007. I think it was 2007 when I joined. And I'm really enjoying this. And because of this COVID-19 situation where everybody gets to stay at home, I've also initiated that we're going to be presenting our club events on YouTube, not on YouTube, but on Zoom, just like we're doing here. So our first event for that is going to be the first Wednesday night of this month, where I'm going to be talking about telescopes and what's up in the night sky for the spring. Does that answer the question, I hope? All right, so
I think it does, and we will maybe at the end, if people are still sticking around, we'll give our other presenters an opportunity to answer the same questions.
Yeah.
We go through a couple more objects, and Mike, I think Mike maybe had a couple more. Is that true,
Okay.
Mike? Mike's on mute.
There you go.
I'm on mute. I'm in the process of recalibrating my scope. I should be ready in
right.
about 5 minutes.
Great.
That'd be good. All right. So
Okay.
just
So,
like
John, so if you'll go for 5 more minutes, then
Yeah.
we'll pop back over to Mike, and then we'll let him close out the evening.
all right. So just like Mike, I'm using the application called SharpCap, and I do the same thing that Mike is doing, and I'm going to show you that in just a minute. This is a picture of M13 that I recently put together. This is the Ring Nebula. Everybody gets to ooh and ah over that one. They love it. Now this one here is called Markarian's Chain, and this is going to be my focus tonight. Here's M84. Here's M86. Over here we have the EYES galaxy. And then this is the rest of Markarian's chain. It goes on and on and on. And then you have other galaxies in the area. If you look really close, here's a galaxy, there's one, here's another one, here's another galaxy. So there's just hundreds of galaxies. This is in the constellation Virgo. Virgo is really famous for the hundreds and thousands of galaxies that you can find out there. So Messier, when he was looking up there, and this was in, I believe, 1781, he found these two galaxies. He didn't really see these others. They were too faint for his telescope. So he saw these two, and he called them M81 or M84 and M86. And that was going to be my focus for tonight. But I want to show you some pictures of the moon that I took. So these are recent pictures of the moon. And I'm really enjoying just putting my camera on the telescope, snapping a quick picture, and then doing a little imaging with it. So it is a little bit out of focus, but what the heck, it works. Now I'm going to switch over and show you what happens when you actually take a picture. Just like Mike, my camera is not working tonight, so I can't even show you in real time. But what I can show you is the pictures that I took last night. So if you look at this, you see a few stars. Doesn't look like much. Now down here we have the histogram, and over here there's stuff happening. So how do we find out? I'm going to click on this guy right here, and it's going to do a histogram stretch is what we call it. And then eventually we're going to see something show up in here, I'm hoping. Yep. So now these bright dots right there are the central core of M84 and M86. And up here, these two bright lights, those are the central core of the stars, the EYES galaxy. So now what I can do here, I've got them all lined up ready to go. So I'm going to click one more time and see if I can't get it to stack at least one more image over here. And so this is how we can pretend like we're actually watching something in real time. Come on, there we go. So we got another image. Now notice we're starting to see some of the other galaxies there, actually the stuff around them. But notice it's really, really noisy in this area. So I'm going to hit this one more time to see if I can't tune in to that area. So this is the area that I want to be able to tune into. Now I can take this line and I can move it up to there, and I can take this one and I can move it over to there, and that's going to make it a little bit more prominent what we're looking at, as you can see. Now we're starting to get it. So at this point, I'm just going to hit this play button, and it's going to go through all 37 images. And watch what happens as it goes through these 37 images. Now, if I were to do this in real time, each one of these images is 10 seconds long. And then there's a 2-second delay between images. So 37 images times 10, that would be 370 seconds, plus 2 times 37, and add another 70 seconds to that, or about 80 seconds. And that's going to be a long time to try to sit here and watch these images show up. Now, when we're all done, we get something that really looks a little bit better. Now, one of the other things that we can do is we can add some other images to this, like what we call a dark image or a dark frame. So when I add the dark frame to this, it's going to enhance this image a little bit more. And I want to click on this over here so I can tune it in a little bit sharper. And we have another histogram over here. So now notice it's starting to show a little darker in the background with each time that we're looking. We're at 12 out of 37 at this point. Now there's another thing that we can do. Up here you'll notice it's brighter at the top than it is at the bottom. And that's called a gradient as it goes from dark to light. It's called a gradient. So you would have to do some extra processing, post-processing, in order to smooth out that gradient. But one of the things that's possible is to apply a flat field. Now a flat field is where you just open the camera up to a light source, not too bright, and you take a series of pictures and then stack them together. So now what that flat did is it gave us a little bit of a darker image, but I'm going to hit this histogram again to try to bring it down. Now this is the linear image right here. So if I click this button, I'm going to give it a logarithmic expansion so that that part that was down here is now expanded out to this area here so that we see a little bit better. Notice the red line, the green line, and the blue line. These are the red, green, and blue aspects of every image. Every camera has red pixels, you know, it only collects red light, blue pixels for collecting blue light, and green pixels for collecting green light. Now ideally, if all of these were one on top of the other, then that would be what we call coincidence, where all the lights are coming together at one time, and it gives a little bit better appearance. Your color comes out quite a bit better when all of these colors are stacked. But the eye is more sensitive.
John,
Yep. Go ahead, Amy.
we have a question for you from Alan.
Sure.
Alan would like, what is the trade-off for picking 10 seconds per image rather than what you have selected?
Okay, so I could have gone for 100 seconds. I could have gone for 1 second. So the trade-off is this. If you'll notice this image over here on this side, this histogram, the color, this white one is called the luminescent or the white band. If there's no black area inside here, then we can't really, you know, it's like you're looking down here to see, do I have anything black? If I turn this off completely and reset everything, now notice my black level is all the way down here. My mid level is here. My white level is all the way at the end. If I move the black level up to here, then that's going to increase the whiteness of the image. And then if I move this mid level down to here, closer to that hump, that increases the brightness of the overall image. Now, the trade-off is this. If you go too high, all the stars will be white. They're going to be blown out and there won't be any color in the stars. If you go too low, then you won't see any of the nebulosity or the detail that's in the galaxy here. So I could have gone to like 20 seconds and that would have blown out these stars. These other stars would be about 3 times bigger than they show up now. And they would all be totally white. So if this histogram right here, if that starts to level off and become, tops out, goes up and then levels off and then drops down again, that means we've saturated the camera for those areas. So right here we see a little bit of saturation. So I want to make sure that the exposure is not so high that it saturates the stars. That's the number one. And then there's another aspect to every camera called gain. You can adjust the gain so that you can use a lower exposure with a little bit higher gain. So the gain is actually a way of letting the camera amplify the signal for you. So if I turn the gain up and let the camera do some amplification, then I can go down in the exposure. So that's where the big trade-off is. And also, the brighter the object, the less exposure that you need. Now, if I had moved that camera to the back end instead of the front end, then it would have changed the entire configuration of the telescope. With the camera in the front, the configuration of the telescope is called an f2. Now, an f2 means that it's a really wide field of view. If I move the camera to the back of the telescope, Now it's configured as an f11. In an f11, I have a very narrow field of view. So a narrow field of view, if I put the camera on the back, all I would see would be this object right here. So if I put the camera in the front, now I've got this wide of a field of view. Now the interesting thing is, the wider the field of view, the less exposure that you need for your camera. That seems counterproductive. You would think that if I had a narrow field of view, I wouldn't need such a big exposure. But you need a longer exposure for a narrow field of view than you do for a wide field of view. So if I put the camera in the back, instead of 10 seconds, it would have been like 5 minutes. That's the difference right there. Any questions about any of this? Here's the eyes
I
galaxy.
think actually Shannon has had you covered. She's been answering questions for us directly on the chat. So so I think we're clear on questions. So John, this is pretty cool.
Yeah.
Just the clarity that you were able to create here tonight. I just think that this is absolutely phenomenal. It's just,
well, I hope I didn't over technical
beautiful
people.
No, I mean, I think you have continued to hold the attention of over 150 people.
Oh, okay.
So, well, 150. And so we don't know how many people that is. We just know that's 150 computers. So, but I think so. If you don't have other additional photos or objects to show us, I think we'll go back to Mike and see if he's got his computer back up and running. And
I'm all done. I'm all done.
Take back over and show us some of his awesome stuff.
Good.
I know we've had a lot of technical things going on tonight. Everyone's sort of been fighting computers.
Yes. and equipment.
Yep, I am ready to go. So I will share.
You are also.
Okay. So hopefully we are seeing my screen. So I think this was a target that I don't remember. I saw it on the list that we talked about earlier. This is the Owl Nebula M97. So we are trying to look at that. So this is the same program that I think it was we were just talking about, SharpCap. So at the moment, I'm just waiting for the image to build. You can start to see this in the middle here, that kind of fuzzy area. You can see the status of what's going on in the live stack down here. At the moment, I've got 2 frames that I was able to capture, and it has ignored 2 frames. So if I look at the part of the sky where the telescope is pointing, it looks like I have some clouds kind of moving in and out. So that might be causing some of these frames to be ignored. Conversely, if we did have something like the satellites we were talking about earlier, if a satellite passed through here, it would cause a streak, and the program wouldn't know what to do with that streak. It would probably throw it out and not stack that particular view either. So you can see we are battling some clouds, and it is giving me, right now I'm not getting that many stacks. But just as we were talking about earlier, I can start to play around with some of these different histograms and to try and tease out some of the views. You can almost barely start to make out kind of the owl face. It looks basically like the head of an owl. You've got basically 2 big round eyes. And again, unfortunately, all we have is 45 seconds worth of that stack. So let's see, we can play around with some of the colors and kind of auto stretch those. And even see if we can get some detail. Yeah, so it's unfortunately throwing away all the additionally stacked views. If I go and I'm just now going to change the what we're looking at. We're actually looking at individual frames that it's being captured, the last one. So it looks like it might be able to start stacking soon. Yeah, it's kind of pointing in some clouds. So that's always the fun part of doing something along these lines. There's always a challenge, whether it's equipment, weather, or sometimes just overcoming the a bit of the knowledge curve. So yeah, unfortunately, we're still stuck with those same three images, but you can almost make it out. This is still something that, unless you were in a really, really, really dark sky, you basically would not be able to detect much of this nebula. It would really just look more like a little fuzzy blob. And with a very large scope, you might be able to start to see some detail in it. So we're starting to get some data coming back. We're gonna have 5 images. And I'm pretty new to SharpCap, or at least I'm still learning some of the ropes. So still playing around with kind of what the best options are for doing some of these stretches. And there we went really green.
Yep, I've seen that before.
Yep. So yeah, it looks like I'm just in too much of a patch of clouds. That's in essence what astronomers like to call that is that was a sucker hole that opened up in the sky. I thought I would be able to move the scope in there and start getting some pictures, but as soon as you get the scope moving and over to something, then the weather decides to change, and you got suckered into looking at it.
Yep, happens to me.
Yeah. So that is what we could get of M97, the Owl Nebula. I'm just trying to see if
Well, and I think that's okay. You know, Mike, we have people saying owl, like that doesn't look like an owl.
The face of
so
an owl. It's supposed to be the face of an owl.
So,
yeah, it's. Yeah,
you see these two little black dots that are the eyes, and then this white fluffy stuff around it. So imagine a white snow owl.
Yeah. Whoops.
Yeah, you know, but you showed the dumbbell earlier, John, and
Yes.
I also always feel every time I see that I'm like, no, it's not.
No.
Some people call it the apple core.
Like, and I know what an apple core looks like.
Exactly right. That's another great one to look at. Is the dumbbell. And unfortunately is not something we can see at the moment.
The apple core.
The apple core,
Yep.
but it really is. It is more of an apple core.
Yep.
And I will say that one of my favorites, and again, it's really it won't come up. In fact, unfortunately, I don't have a good southern view from where I live, my particular house. But the Eagle Nebula is absolutely astounding when you do it in EAA. It's bright enough where you can really play around with some of the details. And I'm just trying to see if I can get a view of that pulled up here.
So while he's bringing that up, I just want to mention that the size of a telescope and the kind of camera that you use have to match. So when you are thinking of going into astrophotography, you say, well, what's the aperture? How big of a telescope do I want in terms of the diameter across the front, the opening? And then when you figure that out, you say, well, that's how much light I want to gather. And then you have to know some specifications about the telescope itself so you can match the camera to go with the telescope. You don't just go grab a camera off the shelf and hope it will work perfectly with any given telescope. That's a
Definitely.
good image of M16.
And especially as we kind of are celebrating the 30-year anniversary of the Hubble telescope, I think one of the most iconic images that the public always remembers is the pillars of creation. And that's actually what we're looking at. Obviously, the Hubble is much clearer, and it tends to be a slightly different orientation. But if anyone ever Googles the pillars of creation, it's these three iconic pillars coming up with these nebula. And that's actually what we're looking at here. Here's one pillar, a second pillar, and a third. Now, from our vantage point, and we don't obviously have that narrow of a field of view that was displayed in that image. This to me looks more like the profile of an eagle. So if you think about the logo for the U.S. Postal Service, you can kind of almost make that out here, where in this darker region, you've got kind of the edge of the wing. You have then down here the body of the eagle, and then you have its talon kind of coming out down here at the bottom.
Just a little bit of clarification on that, Mike, if I may. The wings of the eagle are the red nebula that stretches out from that. And then the tail of the eagle is below that area. The head of the eagle is up and to the right. So that black spot, I used to think that was the eagle's foot, his claw. And the rest of that was his outstretched wings.
Yeah. Okay. See that? It's one of those visual puzzles.
Yes, it is.
But regardless, it's a beautiful. Now,
it is.
I remember the very first time I tried to look at this visually through a telescope. All you really see are the stars, this cluster of stars. You really need special filters and a large telescope to even remotely start to see any of the nebulosity. But employing something like EAA or photograph using astrophotography, you can start to, again, see some of this detail. This was about a 5-minute view, 3 to 5 minutes. And then if we go back to, I'm just hoping, did we get anything more? Yep, I still only have my 5 images yet. And looking up at the sky, I'm completely clouded out in that area of the sky. So
it's either clouds or dew.
Well,
one of the two.
I think that's okay, Mike. We we have actually been going guys, going strong for over 2 hours.
Oh, that's nice.
I actually think I know nobody even realizes that we've been going that long. To actually back I'm going to reclaim here.
No, what I'd like to do, Amy, if I could, I've got one thing that I want to talk about, and that's the size of the galaxies that I was showing relative to the moon, so people can get a real good sense of how big they are. So if you would can you give me control again?
Yeah. Yep, you've got it.
Okay, so I'm going to go back to my screen there so I can give you a clue as to how big these galaxies are. So if we can imagine this galaxy stretches out about that far. Now, if I were to superimpose the moon on this image right here, the moon would be about this big. So you would think, well, if the galaxy is that big, why can't I see it? Well, that's because it's 66 million light years away. That's a good start. It's really dim, so it does take a telescope to be able to see a dim object 66 million light years away. Now, even we have objects that are really close, I mean within like 3 light years away, and they're very, very dim. So you still need a telescope to see a dim object no matter how far away it is. Either it's close or far away. So these stars, every one of these stars that you see are stars in our Milky Way. They are not stars in these galaxies. You cannot see the stars in these individual galaxies. But if we get a really good picture going here, what you will see is brighter spots in some places. And those brighter spots would be star clusters. So that's what I wanted to bring up. How big is the moon relative to the size of these galaxies? The moon would be about this big.
Well, great. Thank you so much, John. So I'm gonna pull back the host from you, and then I am going to for everyone who was Mike talking about the pillars of creation, and everyone, well, that's right there. So that is a Hubble image of the pillars of creation. And when you were looking at Mike's image in red, if this image were turned 90 degrees to the right, that's what you were looking at there when he was pointing out those structures. And this is a really beautiful, excuse me, I'm a terrible host here. One of lost my glasses, there they are on the head. Getting late on the West Coast, it's now morning on the East Coast. And the very last thing I would like to share with you this evening, we were talking about light pollution. And I hope you all can see this. Do you see this image with the palm trees, John? Do you see this?
Yeah, I see that.
Great. So my friend Travis Dio, who works for the University of Arizona at the Mount Lemmon Sky Center, took this photo this evening. And you are looking at the constellation Orion. But you are also looking at rather significant light pollution for Tucson, Arizona. So you can imagine what we would see in this photo, which I imagine he took with his Google Pixel cell phone. And if we didn't have this light pollution, and this is happening even in southern Arizona, where we have the Kitt Peak National Observatory, we have the International Dark Sky Association, we have the Large Binocular Telescope, we have the Mount Lemmon Sky Center, we have the Smithsonian Astrophysical Observatory, and we're riddled with observatories, and we have very well protected skies. So again, I want to encourage you to celebrate the night that we have, and to our friend out there who was watching a Christian channel and accidentally dumped herself into our astronomy star party. I hope
Nice.
that this was interesting for you too. Yeah, that was a giggle there in the chat, but I hope that last few minutes of the star party were interesting for you, and for everyone who stuck with us tonight or stopped by or showed up just now. Thank you so much for joining us and for being willing to hang out with us and talk about the stars. Two you to all of our presenters. You are all amazing, wonderful people to join in on this and to do this for 2.5 hours on a Friday night to bring our communities back together. You know, the Smithsonian Astrophysical Observatory, my biggest passion is reconnecting our communities to the night sky. It is one of the few things that no matter where you are, you have in common with someone else, with everyone else. And so our sign off tonight, I just want to again say thank you and always keep looking up.
Thank you very much,
Amy,
Amy,
so
for
much
bringing
for
us
coming,
together.
and I think we will all sign off.
Thank you so
Thank you,
much.
Mike.
Thanks for having us.
Thank you, Daniel, Brian, John. Thank you.
Good night.
And
Thank you.
good night. So we're gonna sign off. Maybe.